All right, so for those that were able to make it to my office hours, I know a few of you expressed still having trouble with answering number 12 from homework assignment number 2, as I've gotten some emails as well. So for those that might have been confused when we went over this problem in class on Tuesday, this is just going to be another look at how we're solving that. If maybe you weren't familiar with your trig functions that we would have to use to solve this problem. So I'm just going to go ahead and give a bit more of an in-depth explanation if you weren't able to catch it in class. So yeah, let's get into it. Just as a refresher for those that haven't seen this problem in a while, basically we're asked to find the magnitude of the constituent fields of our proton and our electron acting onto point A, which is this area in space. And what this question gives us here off the bat is the displacement, or basically where the electron and proton are oriented on our graph, as well as point A. So I'm going to write some few things down here. We know that our proton is located on the x component at -5 nanometers. And it's obviously at the origin, so there is no y value, which is 0. And then for our electron, we're located at 5 nanometers in the positive direction. And then for our point A, I'm just going to do for A of x, has us here at -17.5 nanometers. And then for the y component, it gives us 6.4. So A of y is going to be -6.4 nanometers. Okay, so when we're trying to figure out the electric field acting on point A, obviously we're focused on these imaginary lines here, so I'm just going to draw them out for you for better visualization. So how we tackle this first, as Dr. Ree mentioned in class, right angles are going to be your friend, and therefore making right triangles whenever you can to show relationships is probably going to be your best bet for tackling these things. So you can see here we can make a right triangle with our origin and our proton. And then you can do the same thing for our electron over here as well. So I'm just going to draw that out. I'll make it bigger just so that's easier to visualize as we continue to solve this problem. So here are our two values, or our two triangles that we have. We have our proton triangle and our electron triangle. And then we're going to work this out from the beginning. This first couple steps are a little bit easy, and then it gets a little bit more complicated, but we're going to go over all of them just so that we have it all nicely together. So the first thing we need to do is figure out what this x and y value is going to be, and what this x and y value is going to be for our electron and our proton. So let's focus first on our proton. I'm going to draw it again down here, just so that we have more room to work with. So we know that if this is the point of our proton and this is point A, question gives us that point A is -17.5 units from the origin, and the proton is -5 units from the origin as far as the x-axis goes. So because we're on the same side of the origin, we're going to just do 17.5 minus 5 to figure out that x value. So x is going to be equal to 17.5 minus 5. That's going to give us 12.5, and don't forget our units, we're working with nanometers. And then for our y component of our proton triangle, that's just going to be flat out 6.4 because all of our other points are at the 0 value for y. So we know that this distance here is going to be 6.4 nanometers, and then our x value for that is going to be 12.5 nanometers. So let's do the same thing for our electron triangle. Oh, okay. It's going to be a bit more like this. And then we were given 17.5 in this direction and an additional 5 in the right direction. So for x of our electron, that's going to be 17.5 plus 5 gives us a nice 22.5 nanometers for our x-axis or x component, and then for our y component of our electron, it's just going to be, again, flat out 6.4, as we start at the origin anyways for our electron. So these are going to be our side values for our triangles. Okay, so now the next step for tackling this is to obviously figure out what these hypotenuse values are going to be, or r squared, because that's what we're going to be working with the most. This is why Dr. B was saying right triangles are going to be your best friend as well. Just seeing anywhere that you can really plug in the Pythagorean theorem and trig functions is going to help you out a lot. So solving for these is going to be a simple a squared plus b squared equals c squared. In this case, it's going to be r squared. So let's work first with our proton. We were given that, we found that our x-axis side is equal to 12.5 nanometers. We're going to square that, plus 6.4 nanometers squared. And when you solve that, you should get an r squared value of, let me double check. What did we get for our math? You should get 1.9721 times 10 to the negative 16 meters squared. Don't forget your scientific notation. I'm just simplifying it for the sake of like looks purposes. I know sometimes when I see that negative or that times 10 to the negative 9th and all that stuff, it can get really confusing. So just don't forget about your scientific notation. So now let's move on and solving this for our electron triangle. So r squared is going to be equal to a squared plus b squared. In this case, we found that our x-axis side is 22.5 nanometers. So we're going to square that plus, again, 6.4 nanometers squared. And that should give you a value of 5.472 times 10 to the negative 16th as well, meters squared. That checks out. Distance-wise, we know that our electron is farther than our proton, so these values seem to make sense. So now we're going to set that aside. We're going to focus now on the electric field portion. Make this bigger. Just highlight these values just so that we can find them easily. We need them. Okay, so recall that when we're working with electric fields, we're going to be using a specific formula for that. That's for electric fields. So E is equal to KQ over R squared. Now, just for a little refresher, KQ are all constant values. We know that K is always equal to 8.99 times 10 to the 9th. And then Q is going to be that value of 1.602 times 10 to the negative 19th. So we're going to do this each for the hypotenuse value for our proton triangle and our electron triangle. Let's start first with our proton triangle. So that's going to be, I'll express it over here. Our total electric field for the hypotenuse of our proton triangle is going to be, same equation setup, so 8.99 times 10 to the 9th. That's going to be times 1.602 times 10 to the negative 19th. Then that's going to be over the r squared value that we got for that question, which was 1.9721 times 10 to the negative 16th meters squared. So when you solve that, you should get the value of electric field equaling 7.31 times 10 to the 6th. So now we're going to do the same thing, but now with our electron. So again, electric field for our electron. We should have the same numerator since everything in our numerator is just constant values. So again, 8.99 times 10 to the 9th. Okay, now for our r squared, we're just using the one that we found over here. It's going to be 5.472 times 10 to the negative 16th. I'll give you a second to work that out on your calculator. So if you're following along, you should have gotten around 2.63 times 10 to the 6th. Then in all of his problems, he will tell you how to round and which place to round to, so don't worry about that. And usually we give you like a margin of like 0.05 or, 0.5, so don't worry too much about that, but just be careful to read for those if they're there. So now that we have our electric field values for our hypotenuses, I'm just going to write that up here so that we remember. So we said that the electric field for our proton was 7.31 times 10 to the 6th. Then similarly, our electron electric field that we got was equal to 2.63 times 10 to the 6th. And that checks out as well. So just a relationship to point out here. Because our point for our proton is closer to our point of interest at point A, the closer that distance is, the stronger that electric field is going to be. Farther away our point is from our electron or from our particle, the weaker that field is going to be. So if we look at our electric field values, even though the value of the distance between the proton and the point A is shorter, we have a stronger value compared to our electron's electric field, which has a longer distance but a weaker electric field. So those numbers check out. We can now move on to the next step of figuring out this problem. Now that we have a value for the hypotenuse electric field, we have to break down and isolate the x and y values of that electric field for each triangle. So in case that was a lot, because I know it's a bit of a mouthful, we found the electric field of our proton, for example, but now we need to figure out of that electric field, what is the value for the proton's x component of the electric field and the value of the electric field's y component for that proton. And this is where our trig properties come in. So the first thing we have to do is identify the degree at which this electric field is acting on point A. So that's going to be this angle right here. And then similarly for our electron, it's going to be this angle right here. And that's because if we just flip this triangle upside down, it would just look like this triangle up here. So just a rule of equivalent angles. So for our first one up here, we are looking for the value of this angle, and considering we already have our opposite side and our adjacent side, going back to our trig rules of SOHCAHTOA, write that out for you, we're going to be using tangent. So if you need a little refresher, this is an easy way to figure out which trig function to use out of which sides you either have or which ones you're looking for. So with our proton triangle, we're looking for this angle concerned next to the proton. So that's just going to look like quick inverse tan. I'm going to copy these triangles down below so we have them for reference. Okay, that didn't work how I wanted it to. Hold on. Okay. There we go. Okay. So remembering SOHCAHTOA, we can take the inverse tan to figure out what this angle degree is. It's gonna look like this. You can enter this into your calculator, and this is a great opportunity to familiarize yourself with how to use these on your calculator because you're definitely gonna wanna know how to do that on the test. We're always gonna do opposite over adjacent, so this is always a numerator, and this one's always a denominator. Numerator, denominator, numerator, denominator. So our numerator is going to be our opposite side, which is going to be 6.4, and our denominator is going to be our adjacent side, which is 12.5, and that's just by using, again, trig properties up here. When you solve that, you should get the value of 27.1 degrees for this angle. So in other words, this is equal to 27.1 degrees. Now let's do the same thing for our electron triangle. So I'm just going to copy this again, and then I'll paste it over on this side this time. So using the same thing, we have a side value for our opposite side and our adjacent side. So inverse tan of 6.4 over 22.5, you should get an angle degree of 15.9. Okay. So now that we have those values, we can figure out the x and y components of our electric field. It was the last thing that we were missing to solving these problems. So let's first focus in on our proton triangle. Let me just write this in here first, 15.9 degrees. Okay. So I'm going back to our trig properties. Let's say we first want to figure out what the x component of our electric field is. So right now we're concerned with this side up here. Using our trig functions, we know that we already have the electric field property, or the electric field value for our hypotenuse. And in this case, if we're looking for our x value here, that's going to be our adjacent side. So it looks like the value or the function that we're going to be using is going to be cosine. And that's going to be for our x. So this is how I'm going to express it. Electric field of our proton for the x component is going to be using cosine. Now, don't get into the habit of automatically assuming that x is always cosine and that y is always sine. It's just relative to how your problems are set up and oriented in space. So just this one thing, don't associate x with cosine and y with cosine. This is just because it happens to be that way for this problem. I've seen a ton of examples where it's flipped, so just some food for thought there. So the way that we want to set it up, as we just went over, tan is equal to opposite over adjacent. So cosine is going to be equal to adjacent over hypotenuse. So in other words, our problem can be modeled like cosine of 27.1 degrees is equal to adjacent side unknown over the electric field value of 7.31 times 10 to the 6th. Now to isolate x, we're just going to do simple multiplication on each side by our denominator. So we're going to move this over here. And that should look like 7.31 times 10 to the 6th times cosine of 27.1 degrees. And you should get an x value of, let's see here, 6.51 times 10 to the 6th. Remember, that's going to be negative since it's acting away from our point of interest. And then when we want to do the y component now for our proton's electric field, we're going to be using sine. And again, that's just because if we look at our trig properties up here, we're looking for our y component, which is opposite of where our angle is. So that's why we're using sine for this case. So using sine, that just looks like sine is equal to opposite over hypotenuse. So sine of 27.1 degrees is equal to an unknown y electric field over 7.31 times 10 to the 6th, which is our hypotenuse electric field. And when you do that, you should get the value of negative 3.33 times 10 to the 6th. So now we've successfully found the x and y components for the electric field of our proton triangle. Now we're going to do the same thing, but for our electron triangle. So the electric field of our electron's x component, same thing, it's going to be cosine for this case because we're looking for the x value, which is adjacent to our angle measurement. So the sine, that's going to look like sine of 15.9 degrees is equal to an unknown x value over hypotenuse 2.63 times 10 to the 6th. Now remember, I got that value from up here. And when you solve that, you should get the value of roughly 2.53 times 10 to the 6th. So that's for our x component. Now same thing for y. Oh my gosh. Sorry guys. I meant to say we're using cosine. Yeah, sorry. So then now for our y component, that's when we use sine. And then again, that's because we're looking at our y component, which is on this side, and that is opposite to our angle measurement. So again, just go over SOHCAHTOA rules, quick refresher, and I think you'll be good on that if you're looking to review right before your exam. So sine, that's gonna look like sine of 15.9 degrees is equal to an unknown y over 2.63 times 10 to the 6th. And when you figure that out, you should get roughly the value of 7.2 times 10 to the 6th. Okay, so now we have 4 values here. We have 2 for our x, which is going to be up here. And then we have 2 for our y, which is going to be down here. So now our next step is to just add our x's and then we add our y's. So for our x's, we had the value of negative, or let me just draw this out first. So our total x component electric fields are going to be the sum of EPX plus EEX. So that's going to look like here, negative 6.51 times 10 to the 6th plus this value right here, 2.53 times 10 to the 6th and when you do that, you should get the value of roughly negative 3.98 times 10 to the 6th. So same thing now for our y's. We're going to be adding the y components of each. And that's going to look like here, negative 3.33 times 10 to the 6th plus this value. Oh, I messed up. That's supposed to be 0.72. Times 10 to the 6th. Okay. And when you add those together, you'll get the value of negative 2.61 times 10 to the 6th. So again, our total x components are going to be equal to negative 3.98 times 10 to the 6th, and our total y components are going to be equal to negative 2.61 times 10 to the 6th. Now, it makes sense that our values are negative, so if you're confused, we can explain it really quickly because we already established that the value of our proton is going to be greater than the value of our electron as far as electric fields go because our proton is closer. Because a proton is pointing away from our point of interest, our values are going to be negative. So if it was the electron that was closer, then these values would be positive. So that's why our values are negative here. And then now the only thing to do is to get a simple, if we imagine this as a triangle, we want to get the quote-unquote hypotenuse of these two values if this was in an a squared plus b squared format. So the way to do that, we know that a squared plus b squared equals c squared. we want to find the individual value of c, we simply put all of that over root. So same thing, we're going to do that, but with these values. Okay, so you put 3.9, and it doesn't matter if these are negative or positive now because we're going to be squaring them, so it's going to be positive anyways as far as magnitude values go. 0.8 times 10 to the 6th squared plus 2.61 times 10 to the 6th squared. And when you do that, you should get the value of 4.76 times 10 to the 6th. And because he wants us to answer, I think the answer said like solve to the 5th power. We just move the decimal over there. So our answer then would be 47.6 times 10 to the 5th. And that is how you solve this problem. So I know it's a lot, but you can see how we broke down, because even though the question didn't necessarily say it, you had to find the x and y components of each of our triangles or of each of our electric fields. So that is all that walkthrough. I can post these as well once I post the video. Hopefully you're going to be able to follow along. I know the work is kind of spread out. But yeah.